Hello friends, today we are going to discuss the chemical bonding and molecular structure. Here I just want to give you the summary of this chapter because already we have discussed chemical bonding. If you have not gone through my videos, then just open my YouTube channel, go in the playlist option in the class 11. In class 11 chemistry you will search chemical bonding, you will get it, all my chemical bonding chapters video, right? So this is an shortcut, or you can say the summary revision terms. What are the important terms of this chapter? As you know very well, this chapter is especially related about the bonds, the force of attraction between the two molecules, how the bond is formed, right? So here you can see the important terms as already discussed here, that which are the important terms. You can see here the ionic bond. You know very well how the ionic bond is formed. Ionic bond is formed with the help of transferring of electron from one atom to another atom, as the electrostatic force of attraction between the cations and anions are formed to constitute an anionic bond. For example, if I talk about the sodium chloride, you know very well sodium chloride, the sodium transfer one electron to the chlorine and chlorine accept one electron, and the sodium chloride bond is formed. To form this both the bonds, we require the stabilizations of energy, that's called lattice energy. The energy released when 1 mole of crystalline compound is formed from its constituent ions. Lattice energy increases with the increase in charge of cations and anions, with decreases in the size of ions. Means as the charge of the cation increases, the lattice energy increases, and as the size decreases. The covalent bond, if I talk about, this bond is formed by the sharing of electrons from the same or different two atoms. Covalent can be single bond, double bond, or triple bond. There is a tendency to complete the octet or doublet by the mutual sharing of electrons. Covalency, the number of electrons of an element that it shares with other atoms. Coordinate bond, the next name of coordinate bond is dative bond. Electrons of shared pair are contributed by one of the two bonded atoms called donor atoms. After the bond is formed, it cannot be distinguished from a normal covalent bond. It is represented by an arrow pointing from the donor atom towards the acceptor atom. If I talk about the examples, then you can see ammonium ion, how the nitrogen accepts one electron from the hydrogen and gives ammonium plus ion. So these were the important terms of the bond. Let us discuss now octet rule. What is the octet rule? As you know very well, the Lewis had given its strengths to acquire. Each and every atom has a tendency or ability to achieve the noble gas configurations or octet or doublet. You know very well the nearest inert gas configuration. Each and every element or atom has a tendency to accept the electrons or transfer the electrons to gain its nearest inert gas configuration and to form the formation of a chemical bond. What are the exceptions of the octet rule? There are many electron deficient compounds were stable, which were not completing their octet. If I talk about the examples of electron deficient compound, you can see here barium chloride, boron trifluoride, and many more compounds which were stable by the central atom has more than 8 electrons. If I talk about the phosphorus pentachloride, phosphorus pentafluoride, sulfur hexafluoride, and iodine heptafluoride. So these were the exceptions of the octet rule. Now let us discuss about the formal charge. Each and every element has different valency or different oxidation state in a compound. So for an atom, the Lewis structure, the formal charge is calculated as valence electron minus lone pair of electron plus half into shared paired electrons. So you can see here how the formula is written, and you can determine by this following. Covalent character in an ionic bond, if I talk about, each and every compounds do not have 100% cationic or anionic, or you can say ionic character or covalent character. So covalent in an ionic bond. In an ionic bond, the cations and anions are not pointed charges. The electron clouds of anion is loosely held as compared to that of the cation. Therefore, it is derived towards the cation under the attractive influence of the cation, and this is called polarizations. As already I told you, the highly electronegative elements, when attract the atoms towards itself, the electronegativity generated, there is some more sort of sharing of electrons cloud. Now this is the basis of origin of covalent character in an ionic bond. The cation is said to have polarizing power and the anion is said to have polarizability. You know very well, if a highly electronegative element comes near the lowly electronegative elements, it has a tendency to polarize itself, means it takes the electron clouds towards itself. So that is called polarizations. And the element or atom which has a polarizing power, that's called cation. The polarizing power and anion is said to be polarizability and cation is said to be a polarizing power. Now let's discuss about the Fuzzen's rule. Smaller the cation, greater the polarizing power. Means as we have a small cation and a large anion, the polarizing power will be maximum. Larger the anion, greater the polarizability. Definitely if we have larger anion size, then there will be a greater polarizability. Larger the charge on cation, greater is the polarizations. Cations with the 18 electron in the valence cell is called pseudo inert gas configuration, causes greater polarizations, and the cations with the 8 electrons in the valence cell, inert gas configuration for the same size and charges. If I talk about the ionic character in a covalent bond, if there is a covalent bond formed between the two atoms of different electronegativity, two shared pair of electrons is more attracted by one of the atoms, it acquires slight negative charge and the other atom acquires slight positive charge. This separation of positive and negative charge develops an ionic character in the bond, and this bond is called polar covalent bond. If you want to calculate the difference of the electronegativity, and if you see the great difference has, the larger the ionic character. If you want to calculate the percentage ionic character, there is a formula of percentage ionic character: 16 into xa minus xb plus 3.5 into xa minus xb whole square, where xa and xb are the electronegativities of the atom A and B respectively. But remember, the electronegativity of first atom should be greater than second atom. This is called Haney and Smith equation. Remember this percentage ionic character: 16 into xa minus xb. xa, the electronegativity value of first atom, and xb, electronegativity of second atom. So in this way you can calculate the percentage character. Percentage of ionic character is equal to 16 into xa minus xb plus 3.5 into xa minus xb whole square. This equation is called Haney and Smith equation. If the electronegativity difference is 1.7, then the bond is said to be 50% ionic and 50% covalent. Remember, if the electronegativity difference is 1.7, then remember that compound will have 50% ionic character and 50% covalent character. Now let's discuss about the dipole moment. The ionic character of a covalent bond can be expressed in the term of dipole moment. Dipole moment mu is equal to q into d. That's q is charge, the value of q 1.6 into 10 to the power minus 19, and d is the distance between the two atoms. So here I have already written where delta q is the charge developed as a result of electronegativity differences, and the d is the distances between the center of the atoms. Dipole moment is a vector quantity. What are the units of dipole moment? Can you tell me? That's a d by, and I hope everybody know the value of d by. 3.33564 into 10 to the power minus 30 coulomb per meter, or coulomb meter you can say. That's a d by. Dipole moment and the geometry of the molecules. Dipole moment is a vector quantity. Difference bond in the symmetrical molecules may give rise to the zero dipole moment because the resultant happens to be zero. So the dipole moment and the percentage of ionic character formula is percentage of ionic character is equal to observed dipole moment upon calculated dipole moment into 100, where the calculated dipole moment is equal to E into D. Observe the dipole moment, that is experimental, delta Q into D, where delta Q is the fractional charges that develops due to the electronegativity differences. So these was about the terms of dipole moment. Now let's discuss about the shape of the molecules. You can see how the molecule shapes can be. That's a triangular, planar, V-shaped or angular or bent, tetrahedral, pyramidal, V-shaped or angular or bent, trigonal, bipyramidal, seesaw shaped, T-shaped, linear shaped, octahedral, square pyramidal, square planar, pentagonal, bipyramidal, distorted octahedral. All these things already I have explained in the valence shell electron pair repulsion theory. If you have not seen that video, then you can just open the channel and you can go through it. You'll have a knowledge about the valence shell electron repulsion theory. I'm giving you a short revision about the valence shell electron pair repulsion theory here also. So let's discuss what is valence shell electron pair repulsion theory. You can see here the electron pairs in the valence shell of an atom, that is bond pair or lone pair. They both form a charged clouds that repel each other, such clouds of charges. Different types of electron pairs suffer different amounts of repulsion. If I talk about the lone pair electrons, they have a maximum repulsion than lone pair bond pair repulsion, and they have more repulsion than the bond pair repulsion. So highest is in lone pair and lowest is in bond pair repulsion. Under the influence of repulsion, the electron pairs adjust themselves in the space where the repulsion is minimum. Means if they have a minimum repulsion, then there is a stability. If you can see just the molecule type like AB2, means here the central atom is A and the bond pairs 2 bonding 2, then there will be a linear shape. If there is a 3 bonding, then there will be triangular planar. 3 bonding but 1 lone pair, then it can be V-shaped or bent and angular. If I talk about 3 bond pair and 1 lone pair, then it will have a pyramidal shape. 4 bond pair and 0 lone pair, then it will have a tetrahedral shape. If I talk about 2 bond pair and 2 lone pair, then V-shaped or bent and angular. If I talk about the 5 bond pair and 0 lone pair, then it will have a trigonal bipyramidal shape. As you can see here, the whole molecule type, bond pairs, lone pairs, and the shape is represented. You can take a screenshot or you can write these things in your notebook, that how the bond pairs, lone pairs give the predictions of the geometry and the shape. As you can see here, the 3 bond pair and 1 lone pair gives pyramidal shape. 2 bond pair, 2 lone pair, V-shaped. 5 bond pair, 0 lone pair, trigonal bipyramidal shape. 4 bond pair, 1 lone pair, seesaw shaped. 3 bond pair, 2 lone pair, T-shaped. 2 bond pair, 3 lone pair, linear shape. 6 bond pair, 0 lone pair, octahedral shape. 5 bond pair, 1 lone pair, square pyramidal shape. 4 bond pair, 2 lone pair, square planar shape. 7 bond pair, 0 lone pair, pentagonal bipyramidal shape, and 6 bond pair and 1 lone pair, distorted octahedral shape. So these are the shapes which we can predict according to the valence shell electron pair repulsion theory. If I talk about valence bond theory, the overlapping of atoms, orbitals of valence shell of atoms lead to the formation of covalent bond. Orbitals containing 1 electron can participate in overlapping, leads to increase in electron density in the region between the 2 moles, which increases the attraction. Strength of the bond forms depends upon the extent of overlapping. Orbitals with more directional nature, p orbitals, undergo the stronger overlapping than orbitals with the less directional nature like s orbitals. Ends on the overlapping leads to the formation of sigma bond, and the sideways overlapping leads to the formation of pi bond. Remember those 2 concepts as already I have discussed you in the valence bond theory video. You can just open my channel and you can look to the valence bond theory video. Here just is a shortcut revision about the valence bond theory. So according to this theory, overlapping of the atoms, orbitals of the valence shell of atoms leads to the formation of covalent bond. Overlapping of atoms, orbitals of the valence shell of atoms, this leads to the covalent bond formation. Orbitals containing 1 electron can participate in overlapping, and overlapping leads to the increase in electron density in the region between the 2 moles, which increase the attraction. Strength of the bond depends upon the extent of overlapping. Orbitals which have more directional nature, that's called p orbitals. It can have x direction, y direction, z direction. It undergoes stronger overlapping than the orbitals which are having less directional shape like spherical shape of s orbitals. And on overlapping leads to the formation of sigma bond, and sideways or lateral ways gives the formation of pi bond. End-to-end overlapping, sigma bond, it can be formed independently, it can be stronger bond, it can be greater overlap, and it has a free rotations. If I talk about the pi bond, then pi bond will be sideways overlapping. It can be formed only after the sigma bond formation, means singly pi bond can't be formed if there is 2 bonds Bond order is 2, then one will be sigma and one will be pi. If there is only one bond, then there will be only formation of sigma, no pi bond is formed. Pi bonds are the weaker bonds, they are having a less overlap, and their free rotation is not possible in the pi bonds. Now let's discuss about the hybridization. It is the process of intermixing of orbitals of the same atom having similar or slightly different energies to give rise a new set of same number of orbitals having equivalent shape and energy generally at the time of chemical bonding. Just remember the intermixing of orbital, or you can say when the two pure atomic orbitals mix to form an impure orbital, that impure orbital is called hybrid, and the process is called hybridization. So here it's generally written in the chemical bonding, there is a mixture of different orbitals having the same atoms and similarly slightly different energies. So this gives the formation of hybridization. Hybridization shape and hybridization you can see here. If the geometry is linear, then there will be sp hybridization, 180 degree bond angle, and examples are beryllium chloride, sp2 triangular planar, bond angle 120 degree, boron trifluoride, sp2 tetrahedral, sp3 tetrahedral, 109 degree 28 minute, methane example, sp3d trigonal bipyramidal, 90 degree and 120 degree, phosphorus pentachloride. If I talk about octahedral, sp3d2 octahedral, 90 degree angle, sulfur hexafluoride, sp3d3 pentagonal bipyramidal, 90 degree and 72 degree bond angle, iodine heptafluoride, and dsp2 square planar, 90 degree bond angle, that is tetranickellite 2 ion. So these were the regular shapes of hybridizations. If I talk about the distorted shapes, so you can see this table of the distorted shape. Tin chloride, sp2 hybridization, bond pair 2, lone pair 1, V shape. Ammonia, sp3 hybridizations, bond pair 3, lone pair 1, pyramidal shape. Water, sp3 hybridization, 2 bond pair to lone pair, V shape. Sulfur tetrafluoride, sp3 hybridization, 4 bond pair, 1 lone pair, seesaw shape. Chlorine trifluoride, sp3d hybridization, 3 bond pair to lone pair, T-shaped. Xenon fluoride, sp3d hybridizations, 2 bond pair, 3 lone pair, linear shape. Xenon oxytetrafluoride, sp3d2 hybridization, 5 bond pair, 1 lone pair, square pyramidal shape. Xenon tetrafluoride, sp3d2 hybridization, bond pair 4, lone pair 2, square planar shape of the molecule. And xenon hexafluoride, sp3d2 hybridization, 6 bond pair, 1 lone pair, distorted octahedral formation. If I talk about the resonance, a single Lewis structure sometimes cannot represent the true electronic structure of a molecule. Resonating structures is used to represent the true electronic structure. This Lewis structure are then called canonical contributing or resonating structures, and the real molecule is considering to be resonance hybrid. The molecule itself exists in a single unchanging state intermediate between the resonance structure. The molecule is the only partially described by one of the canonical structures. That resonance hybrid are always more stable than any of the canonical structures. The delocalized of the electrons lowers the orbital's energy and provides you the stability. The gain in the stability of the resonance hybrid over the most stable of the canonical structure, that is called resonating energy or resonance energy. A canonical structure that is lower in energy make a relatively greater contribution to the resonance hybrid. If I talk about the hybridizations of the ions like sulfate ion will have a sp3 hybridization and the shape tetrahedral, lone pair 0 electrons. Carbonate, sp2 hybridization, triangular planar, lone pair 0. Nitrate or NO4, sp2 hybridization, triangular planar, lone pair 0. I3 minus, sp3d hybridization, linear, 3 lone pair. ICl2 plus, sp3 hybridization, V-shaped, and 2 lone pair. So this was our resonance and ions hybridization. Now let's discuss about the MOT, that's called molecular orbital theory. Molecular orbital theory by the Hund and Mulliken. In atoms, all the orbitals are involved in bonding, not only the valence orbitals. Atomic orbitals merge to give rise to a new set of molecular orbitals, that is called molecular orbitals are formed. by LCAO, linear combinations of atomic orbitals. Bonding molecular orbitals and anti-bonding molecular orbitals are formed. Bonding molecular orbitals are formed by the constructive interference of the electron waves. Psi square is equal to psi square A plus psi square B plus 2 psi A into psi B. Probability of finding the electron is more, less energy, more stable, and favors the bonding in bonding molecular orbitals. In anti-bonding molecular orbitals, it is formed by the destructive interference of the electron waves. Psi square is equal to psi square A plus psi square B minus 2 psi A into psi B. Probability of finding the electron is less, more energy, less stable, opposes the bonding. Bond order formula: half into number of bonding electrons minus number of anti-bonding electrons. NB and Na means, NB means number of bonding electrons and Na means number of anti-bonding electrons. If I talk about the bond order, greater is the bond energy, higher the bond order, lesser the bond length. Means bond order is inversely proportional to bond length, or bond length is inversely proportional to bond order. Less bond length, more bond order, more bond length, less bond order. You can see the molecular orbital diagrams as the energy increases from 1s, 2s. You can see the nitrogen. This is the bond order of nitrogen molecules. Hydrogen, you can see 1s2, 2s2 and 2p3. This is the N2 molecules, and this is O2 molecules. So you can see here in the bond order is equal to half into Nb minus Na. Number of bonding electrons, you can see here the downside one, these are the bonding electrons, and upside one, these are the anti-bonding electrons. So you can see here total bonding electrons 2 to 4 and 4, 8 and 2, 10. So 10 bonding electrons and anti-bonding electrons 2 to 4 and 0 means 10 minus 4 upon 2. 10 minus 4 upon 2, that is 6 upon 2, that is 3. So nitrogen I will have triple bonding, that is no unpaired electrons. It is a diamagnetic, and the molecular orbitals for the different nitrogen molecules or different molecules, you can see here the bonding electrons and anti-bonding electrons. This is the table by which you can remember which of the atoms are diamagnetic or paramagnetic. Order of stability, if I talk about, N2 is greater than N2 plus, which is equal to N2 minus, which is greater than N2 minus. And you can see here about the oxygen, O2, O2 plus, O2 minus and O2 3 minus. Superoxide and peroxides also, and the bond order of stability, O2 plus is greater than O2, is greater than O2 minus, is greater than O2 2 minus. So this is molecular orbitals theory diagram, as you can understand. Now let's go ahead. You can see here hydrogen bonding. You know very well the molecules involving a hydrogen atom bonded into a very small but highly electronegative atoms such as fluorine, oxygen or nitrogen experiences a special type of attraction called hydrogen bonding. This bond is represented by a dotted line. Hydrogen bonds are much stronger than the ordinary van der Waals interactions. These are much weaker than those type of ionic or covalent bonds. Association in water, if I talk about, the oxygen atom of the water molecule can form two hydrogen bonds. Each oxygen atom is joined to four neighboring hydrogen atoms in a tetrahedral arrangement. Two hydrogen atoms are linked covalently, and other two hydrogen atoms are associated by the hydrogen bonding. The structure of ice is rigid but open. The presents a cage-link framework. The molecules are not packed very closely together, and there are the vacant spaces present in the structure. As ice melt, some of the hydrogen bonds are broken and the open cage-like structure collapses. The volume increases and the density decreases. Density increases, volume increases and density increases. Water therefore has a greater density than the solid ice. Ice floats on liquid water. With the further increases in temperature, the density continues to increase due to the breaking of more and more hydrogen bonds. Liquid water attains a maximum density at 4 degrees Celsius and above 4 degrees Celsius. Kinetic energy of the molecule increases and the molecules move apart. This causes the expansion. Therefore, the density of the water starts decreasing again. There are two types of hydrogen bonding, as you know very well: intermolecular hydrogen bonding and intramolecular hydrogen bonding. The formation of hydrogen bonds between the two or more molecules of the same or different substances is known as intermolecular hydrogen bonding. As for example, water molecules, hydrogen bonding may occur between within the single molecule. This is known as intramolecular hydrogen bonding. As you can see here, orthochlorophenol, orthonitrophenol, salicylic acid, chloral hydrate. Orthonitrophenol is more volatile than the paranitrophenol because in orthonitrophenol there is intramolecular hydrogen bonding, due to which it has a lower boiling point, whereas paranitrophenol shows intermolecular hydrogen bonding. So the two types of hydrogen bonding, intermolecular and intramolecular hydrogen bonding. As you can see, the intermolecular hydrogen bonding in water, and if I talk about the intra, you can see in orthonitrophenol or paraphenols. So this is our revision of chapter number 4, chemical bonding. Hope all of you have enjoyed.